All right, class. So this is a recording of section P2, which is on the law of total probability and Bayes' rule. And I decided to make this recording so that you can study it on your own, and you can see it more than once. And I will also give you a couple of examples of how to do this. So let's get started. I will share the screen with you. Okay, there we go. So this is again section P2, tree diagrams and Bayes' rule. So let's get started. All right. So let's just review a couple of the probability rules we've learned so far. This is called the addition rule, which says the probability of event E or B is equal to the sum of the probabilities of A and B minus the joint probability of A and B. And this minus here is for events A and B that are not disjoint. And therefore, when we are adding A and B, we are double counting the joint probability. So that's why we subtract one of these, A and B's. This, of course, is the multiplication rule, or at least one version of it. It says the probability of A and B is equal to the probability of A times the probability of B if A, which is the conditional probability of B if A. This is the complement, which says the probability of not A is equal to 1 minus the probability of A. This is the conditional probability rule, which we're going to talk more about today. Probability of A if B is equal to the probability of A and B divided by the probability of B. And by the way, if it's in reverse, if it's the probability of B if A, then the numerator is the same, but the denominator becomes the probability of A. And then these special cases, disjoint means that there's no elements in common between events A and B. In other words, they cannot occur at the same time. So the probability of A or B is simply the sum of probability of A plus probability of B. And then the independent one says that if A and B are independent, that means knowledge of one of the events does not change the probability of the other event. For example, the probability of B if A is simply the probability of B. And then if we wanted to find the probability of A and B, we simply multiply the probabilities A and B if they're independent. This is something we did in class last time. We have a red die and a green die, and let R be the event that the number of spots showing on the red die when it's thrown is 3 or less, and G be the event that the number of spots showing on the green die is more than 3. The events R and G are, and the answer is independent. Now, you might have thought, disjoint, but they're not disjoint because these are two separate dies. So it's perfectly fine that when you roll both dies together, that you could have on the red die you could have 2, and on the green die you could have a 4, and that's perfectly that can happen together, and therefore they are not disjoint. But they are independent, which means that whatever result you get on the green die or the red die does not affect the result on the other die. All right, so the answer is independent in this case. Now, sometimes people like to use what's called a tree diagram to illustrate certain type of probability problems. And also we're going to review the total probability. All right, okay. So, and also there's a special case of the conditional probability called Bayes' rule. All right. And then we did this in class last time. So suppose a regional airport is serviced by 2 airlines. Airline C runs 70% of the flights and is late 20% of the time. Airline D runs the rest of the flights at the airport and is late only 10% of the time. What proportion of flights at this airport are late? So the probability of being late is the probability of late and it being airline C, or, which is a plus, these are disjoint, the probability that you're late at airline D. There's only two airlines, A, C, and D. And so the probability of a particular flight, we choose a flight at random being late, is the sum of these two probabilities. And then we use the multiplication rule to answer this question. Okay, so the probability of late and C would be the probability that we have airline C times the probability that you're late if you've taken airline C, plus this probability, the second one is the probability that you are using airline D. That's times the probability that you're late. You're using airline D. So for the first probability, it would be 0.7, which is the probability that you use airline C, times 0.2, which is the probability that you are late, given that you're using airline C. And then this probability is 0.3, which is 30% probability that you use D, times the probability of which is 0.1, which is the probability that you are late, given that you've taken airline D. All right, so that's how you do it. And you can also use what's called a tree diagram to illustrate this. So this is how you do it. Okay, so to answer this question, what's the probability that you're late? Well, it's actually the sum of these two probabilities. Or excuse me, not the sum of these two probabilities, but it's a sum of two probabilities that you'll be calculating. Now notice here in this tree diagram, you have C and D. C is the 0.7 is the probability that you have taken airline C. 0.3 is the probability of taking airline D if they are the only two choices. Now, looking at this branch of the tree here, the C branch, notice it branches out into late and not late. Now, 0.2, that is the conditional probability that you're late, given that you've taken airline C. All right, makes sense, right? This is the conditional probability. And then 0.8, which is 1 minus 0.2, is the probability that you're not late, given that you've taken airline C. And very similar idea down here with airline D. 0.1 is the probability that you're late, given taking airline D. 0.9, which is 1 minus 0.1, is the probability that you're not late, given airline D. So how do you answer the question about what's the probability of being late? Well, one thing you want to do is multiply across these branches. Now, this 0.14 is 0.7 times 0.2. And this is the multiplication. So the probability of C times the probability of airline C times the probability of that you're being late, given that you've taken airline C. You multiply those two. 0.14 is the joint probability that if you picked a flight at random, that the flight is with airline C and it's also late. Similarly, if you multiply 0.7 times 0.8, is 0.56, is the joint probability that if you picked an airline at random, that airline would be airline C and it would not be late. And then the same thing down here. This is the branches that deal with airline D. And if you multiply 0.3 times 0.1, you get the probability that if you selected an airline, a flight at random, that the flight would be with airline D and be late. And also, if you multiply 0.3 times 0.9, which is 0.27, that's the joint probability that if you picked a flight at random, it would be both with airline D and not be late. So, if you wanted to answer the question using this tree diagram, what is the probability of if we picked a flight at random that would be late, it would simply be the sum of the lateness with airline C, which is 0.14, plus it being late with airline D, the joint probabilities here. If you add these two up, it's 0.17. That's your answer. All right. Now, this particular slide deals with health cases and with diagnostics. So you may or may not have a disease. You take a diagnostic test to see if the test tells you that you may have this disease. These diagnostic tests are not foolproof, so they could be wrong. So you could make it. You could have an error. So what kind of errors do we have when we take a diagnostic test? Well, if the diagnostic test says that you have a disease, which is a positive result, it's possible that you don't have the disease in actuality. So that's a false positive. On the other hand, if the result says that you don't have a disease, but you actually do have a disease, that's called a false negative. All right, so many times when we want to calculate probabilities using false positives, false negatives, then we use the conditional probability. All right, so let's look at this for example. It says, suppose that 3 in 10,000 people have a certain disease. So so if you say, let me just check something here in terms of what they use. So they use the event S for a disease. So 3 in 10,000, if you divide that, you get 0.0003. And that's the probability that if you pick somebody at random from the population, that they would actually have this disease. Now it says in a test for the disease, diagnostic test, positive result indicates the person may have disease, and a negative result generally means the person does not have disease. However, the test gives a false positive, all right, 4% of the time. Now, what does that mean again? That means that the test is saying you have the disease when you don't, all right? And it gives a false negative 1% of the time, which means that the diagnostic test says you don't have the disease when you actually do. So these are false readings by the test. All right, so let's see if we can figure out what exactly the results are when we use a tree diagram for this. All right, so you can set up the tree diagram. The first thing that we want to determine is the probability actually having this, which is 3 out of 10,000, 0.0003. And then the other would be the probability of actually having or not having the disease. So it's the probability of having it. Probability of not having it would be 1 minus that, which would be 0.9997. That's what the H here would be. Now, the P means positive result for your diagnostic test. The N means negative result. So a false, if you have a false negative, that means the diagnostic test says no, but you actually have a disease. So in the tree diagram, the 0.01, which is 1 out of 100, would show up here. All right, I hope you understand what this means. This is the probability of the test saying no when you actually have a disease. That's the false negative. The false positive is 4 out of 10,000, which is over here. And I think this probably, no, wait a minute, is this right? Let's go back. No, it's 4%, that's right. So 4% is the false positive, all right? Now, what's a false positive mean? It means you get a positive result, but you actually don't have disease. So that would be along this branch here. That would be 0.04. So the 1% is the false negative, and the 4% over here is the false positive. Now, the question, of course, would be, can you fill out, given this information, can you fill out all the rest of this? And the answer is yes. using the laws, the multiplication laws, using the complement law. And let's just quickly run through that. For example, along this branch here, you know that 0.0003 is the probability that you have the disease in the population. Now, can you figure out all these other possibilities up here? And the answer is yes. And how do you do that? Well, if 0.01 is the probability that the diagnostic test says you don't have the disease, all right, given that you really do, then the positive result along this branch here must be 1 minus 0.01 or 0.99. Okay? And then if you multiply 0.0003 times 0.9, that would give you the probability that if you pick somebody at random, they have the disease and they got a positive result. Notice there was no error. 0.0003 times 0.01 would give you the probability that you pick somebody at random and they got a negative result, diagnostic result, and they do have the disease. So, and you expect a small probability. Now down here, you can also fill out all the other probabilities here. For example, H is just H is the probability in the population that you don't have this disease. And it's just 1 minus 0.0003. It's 0.9997. And then down here, this is the probability that you have a negative result in your diagnostic test, given that you don't have the disease. Simply 1 minus 0.04, which is 0.96. And then if you multiply 0.9997 times 0.04, you get the probability that if you select somebody at random, that they don't have the disease and they got a positive result. And then if you multiply 0.9997 times 0.96, you get the probability that a person, if you pick the person at random and they don't have the disease, they get a negative result from the diagnostic test. Okay? So the first one is where the question mark is. It would be simply 0.0003 times 0.99. Okay. So you have to figure out what the number must be. And I have a calculator with me. Let me just see what the answer to that would be. Actually, I'm sorry. The question mark here would be simply 0.99. So it's B. All right, that's the answer to P, because it's 1 minus 0.01. For this one here, they're asking what the answer is here. This is 0.0003 times 0.01, and that would mean 5 zeros before the 3. 1, 2, 3, 4, 5. It's this one here, A. And this is the full, and this is the example with the flights. You could have used this tree diagram to talk about the flights. The flight example we saw before, where 70% of the flights in a given airport were with airline C, 30% with airline D. And then they said if you took airline C, the chance that you were late is 20%. And if you took airline D, the chance that you were late is 10%. And you could fill out all the rest of this using the same idea. Okay. And by the way, this one here, this is the second case where we looked at the false positive, false negatives. If you want to know what's the probability that you pick somebody random and they have a negative diagnostic test, then it's simply the sum of these two numbers here, down here, these two numbers. So the law of total probability, if you have a bunch of events that are disjoint, all right, and together make up all possible outcomes, then you could simply say that the probability, now this is B1, B2 through BK, the probability of another event, A, occurring, and let's say A only occurs if one of these other events occur. Okay, then probability of A is simply the probability A and B1 occurring, or the probability of A and B2, or the probability of A and B3, all the way up to the probability of BK. So it's simply these are all disjoint probabilities. That's called the law of total probability. All right, so sometimes you have to use the law of total probability to calculate probabilities. So, for example, if 1% of women at age 40 who participate in routine screenings have breast cancer. So 1% of women at age 40 who participate in routine screenings have breast cancer. 80% of women with breast cancer get positive mammograms. 9.6% of women without breast cancer get positive mammograms. All right. So they give you those three pieces of information. And then they say a 40-year-old woman participates in routine screening and has a positive mammogram. What's the probability she has cancer? So how would we say this in another way? We would say this is the probability of an individual who has, so basically it's the probability of a person having cancer, women having cancer, if we know for a fact that they had a positive mammogram. All right. All right. So what's the following is the conditional probability that would answer this question? It's the probability that the person they have cancer if they have a positive mammogram. Okay. Let's go back actually see it again. What's the probability she has cancer? I'm sorry. So actually, we're just asking the question, what's the probability of having cancer? So that's it. All right. Which of the following is the conditional probability that would answer this question? It is not a conditional probability. So it's a trick question. So what's the probability she has cancer? That's simply E. Now, to calculate it, you may need to use conditional probabilities, but the point of that is that they're just saying what's the probability she has cancer. That is the question we're going to answer, the E. And it's not a conditional probability, ultimately. Okay, so what they're doing here is they're saying, let's build a tree diagram, which will help us answer the question. So we know for a fact that, let's go back actually before we do this. Let's go back to the question. What type of information were we given? We know that the probability in the population, well, let me say this again. We know 1% who participate in routine screening have breast cancer. So that's the probability that they have breast cancer if they're involved with screening. Okay. 80% of women with breast cancer get positive mammograms. 9.6% of women without breast cancer get positive mammograms. Okay. So let's just look at the 1%. Let's go back to what we're doing, the tree diagram. Okay. So it says here, we're using 1% as the probability that a person has cancer in the population. Let me actually look at that. Not sure if that's correct. Let's go back. Okay. Now this is a little tricky in the wording, so I just want to make it clear to you what the wording is saying. The population that we're looking at are women who are screening for breast cancer. Okay. So this is the population. It's not all women. It's the women who are screening for breast cancer. That is the population we're looking at. So women who participate in routine screening, 1% of those actually have breast cancer. All right. So that's the trick here. The routine screening is not a conditional probability. It is the population itself. So we have all these women we could just say, let's say there's 50 million women who routinely have who routinely screen for breast cancer, and that is the population we're looking at. So 1% of those would, in general, be those who have breast cancer. So that would be 1% would be the answer to that. That means 99% of women who participate in routine screening do not have breast cancer. Now, 80% of women with breast cancer get positive mammograms. Okay, that's a correct result, right? Because if you get a positive result, it's indicating you may have breast cancer, and what these women do. So 80%. So 80% of women with breast cancer get positive results, get positive mammograms. 9.6% of women without breast cancer get positive results. That's a false positive. That's a false positive. So let's go back to so these three numbers will show up on the tree diagram. Okay, so you see up here that the 80% is the correct amount, correct percentage of women who have cancer who receive positive results. That's the correct reading. That's what this number is here. The 9.6% is that's the false positives. That's if people get a positive result if they don't have cancer. That's where the 0.016 shows up here. The 0.01 is the percentage, the 1% of women who are routinely screening. So we have three numbers. Typically, three numbers are all that we need in this type of breast cancer. And so how do we get this number, which is 1 minus 0.01, 0.99. That's 99% of the women don't have breast cancer. If 9.6 of the women who don't have breast cancer have a positive result, that means 1 minus that, or 90.4%, 0.904 of the women get a negative result if they don't have breast cancer. And then up here, 80% of the women who have breast cancer show a positive result. And it's 1 minus that, 20% of the women will show a negative result if they have breast cancer. All right. And so we can answer, once we have the tree diagram set up like this, we can answer questions. Now we simply just multiply through using the multiplication rule. And this number here, 0.008, is if we pick a lady at random, 40-year-old lady at random, or person over 40 at random, who does have cancer and did get a positive result from the mammogram. That's the probability that if we pick somebody at random, that they would have both those cases. That's the 0.8% or 0.008. We multiply these numbers across 0.002. That's the probability if we pick somebody at random, they would really have cancer and they would have a negative result. And then these two numbers we multiply through, we get 0.99 times 0.096. That's the 0.09504 is the probability that if you pick one of these women at random, they would not in reality have breast cancer, but they would have a positive diagnostic test. And then if you multiply these two numbers, 0.89496, this is the probability that if you pick a lady at random, they would not have cancer in reality, and they would also have a negative diagnostic test. So if you wanted to know what's the probability that you selected the lady at random and they would have a positive result, then you simply add these two here because these are the two possible positive results. Okay. Now Bayes' rule is just an elaboration of the conditional probability. And it's useful to know Bayes' rule if you're being asked to find a conditional probability when the in the reciprocal inverse probability is what's given. Problem. I'll tell you what I mean by that in a minute. All right. So here's the we have four different events here, A, B, C, and D. And we're interested in the probability that it's the probability A of D. So the probability A of D is simply the numerator is the joint probability of A and D, denominator is probability of D. Okay. Okay. Seems like we are stuck here for a second. Here. So just give me a second. There. Now the numerator can be expressed with the other multiplication. That is the rule where you get the reverse conditional probability. Notice the probability here is probability A of D. You could have the other multiplication rule where you have probability of D of A. And remember, the probability of A and D could either be the probability of A given D times the probability of D, or the probability of D given A times the probability of A. All right. So if, for example, you're being asked to find one of these conditional probabilities, but the problem, the information that you're given, gives you the other conditional probability, the one in reverse, then Bayes' rule is useful. So what we do is basically the numerator of the conditional probability, we convert that to the other multiplication. That is the probability of A times the probability of D if A, because this is the reverse of this one. And the denominator, we're going to use the total probability. Okay. So the denominator is going to be the probability of A and D and the probability of not A. And then in the denominator, we simply convert the these into the multiplication rule. Using multiplication rule, convert this into this. And notice again, this looks like the numerator up here, which it is. Same thing. And then the other piece here, the probability of not A and D. This is just not A and D, the event D, is simply the probability of not A times the probability of D if not. Okay. All right. Now this is a little complicated, but if this formula confuses you, you can always use the tree diagram. The tree diagram is going to give you the answer. Okay. So who came up with this Bayes rule? It's the Reverend Thomas Bayes back, I believe, in the looks like the 18th century, 1702. He was born, and died 1761. He was a clergyman, but was a mathematician also. Yeah, start. There we go. All right. Now, this is just a reinstatement of what we said earlier, and I can tell you that most of these slides here you can go through yourself. It will explain why the probabilities show up as larger or smaller in a particular problem. And I'm not going to actually ask you in homework or an exam why this probability is small when you might think it's big or vice versa. But you can read through this on your own just to get an idea of why probabilities show up as they do. So I'm not going to spend time on that. It's an interesting, there's interesting reason for everything. So, but I'm not going to, again, want to spend time on this. I just want to give you enough information so you can solve problems. All right. So this section in here, you could just read through on your own. And again, it'll explain why these numbers are large or small when you use it. Bayes' rule again, this is it. and it's complicated. It looks complicated, but it's actually pretty easy to use. And once again, if you don't want to use it, you can use tree diagrams to solve problems, and I'll show you how to do that in a couple minutes. So I'm going to give you a couple of examples. Just give me a second. Okay, and this is another example of how to use Bayes' rule. And there's plenty of examples that you can look through here. So the textbook itself will tell you how to do this. It looks very complicated. And then it shows you how to solve a problem using tree diagram. So what I'm going to do next, again, I can spend all day showing all these. You're just going to get confused. Just know that Bayes' rule is just an elaboration of the conditional probability equation. Tree diagrams can be used in place of the multiplication, the actual formulas if you want to use tree diagrams. So what I'm going to do next, I'm going to unshare this. And I'm going to share with you two problems that are in the book. And actually, let's go back to the book just for a second. Actually, I want to go to the book in a minute. So let's go to, just give me a second. I will help you out in terms of getting, let me just see here. Hold on a second. Here we go. So let's see if I can actually find the actual e-textbook. Here we go. This is the e-textbook. So I will share it in 1 second. Just give me a second here. Here we go. Okay. So what I'm going to do is come back to you guys, and we'll share the screen. And share the textbook itself. All right, so we're in P2. And what we're going to do is go to the end of the section where there's actually some problems. Just give me a second. Let me find these problems. Here we go. So let's read through the problem first. And you should also, when you review this video, make sure that you can open up the textbook, the e-textbook, and get to the particular page where the problem is so you can read through it as you are going through the problem with me. So let's read through this. This is P55, and it says, according to the U.S. Census, 65% of housing units in the U.S. are owner-occupied, while the other 35% are renter-occupied. All right, so it's pretty easy idea, right? So you have housing, and 65% of those houses are owned by people, owned by the occupants, and 35% are occupied by renters, not the owners. Now, what you see below here in this box here are conditional probabilities. Now, this is a little different than what you saw in one-way and two-way tables before, so you have to be careful with this, how to read it. It says conditional probabilities of the number of occupants in U.S. housing units. So what are these probabilities or proportions actually are probabilities of? So for example, there are 6 of these numbers here. Now, running across the top here, it says 1, 2, and 3 or more. That's a number of occupants in the housing. So 1 means that that house only has 1 person. 2 means 2 people in it, and 3 or more means 3 or more people are living there. Okay. Now, owner occupied, of course, means that people who are living there are owners, and renter occupied means people living there are renters. And so what's the 0.217 say? Well, it says, what's the probability that you have 1 person in the house, given that that person is an owner? Okay, 0.362. That's a probability of 1 owner in the house, given that you know that the person's a renter. And the 0.363 is the probability that you have 2 people in the house, given that you know that the people in the house are owners. And then, or when they say owners, that means owners or family of the owners. And then 0.261 is the probability of 2 people in the house, given that you have 2 people in the house, given that they are renters. And so forth, with the 3 or more to look at the same way. All right, so this is set up really, these numbers, the points, the 65% and 35%, and then these numbers here are set up so you can do a tree diagram. Okay, and let me show you what the tree diagram is in a minute. I'll show it to you in a minute, but I want to show what the questions are first, and then we'll go to the solution and show you the tree diagram and how you can answer these questions using. So the first question is, what's the probability that a U.S. housing unit is rented with exactly 2 occupants? All right, so that is basically, if you chose a housing unit random, you just want to know what's the probability that 2 people are living there. All right, and that there is rented with exactly 2 occupants. All right, what's the probability that a U.S. housing unit is rented with exactly 2 occupants? Now, what does that mean? That means you're selecting a housing unit random. You don't know anything about it. You want to know what's the probability that that particular housing unit is rented and exactly 2 people were living. B, what's the probability a housing unit has 3 or more occupants? That's all they're asking for. Select a housing unit random. What's the probability that 3 or more people are living there? They're not asking specifically about renting or owning. They're just saying, what's the probability that in that housing unit, 3 or more people are living? And finally, the final probability is, what's the probability that a unit with 1 occupant is rented? This is a conditional probability. They're asking, what's the probability that what's the probability that the housing unit's being rented, given that you know there's only 1 person? All right, so let's look now. I'll stop sharing this. And let's share the solution screen. All right, now, as with other probability problems, as I showed you in class, it would be helpful to use capital letters or even numbers in this case here, if they're useful, to represent events. So this is the letters that I use. I use the letter W for owner, occupied, housing unit. I didn't want to use O because it looks like a 0. So I decided to just use W, which is a letter in the word owner. It's just my choice. The event R for renter. It means renter occupied housing unit. The event 1 means 1 person's living in the housing unit. The event 2, 2 people are living in the housing unit. The event 3 plus means 3 or more people are living in the housing unit. Okay? And what do we know? We know these 2 probabilities. The probability that if you picked a unit at random, that it would be owner occupied, and that would be 0.65. Probability that would be renter occupied would be 0.35. And then that table I showed you will provide all the rest of the numbers that we need. So we can use a tree diagram. We're going to start off with the unconditional probabilities. That's the probability of owning versus renting. That shows up first. Now up here is if a person is owning the property, what's the probability that it's only one person living? And that was the first, if you remember, or you may have to again look in your book. That's the very first number, upper left in the table. There's 6 numbers. It's the first one upper left, and that's 0.217. And then the second number would be what's the probability that 2 people are living in that unit if it's owner occupied. And then if you just go to the column that shows 2, again, the owner occupied row, that's 0.363. And then the probability, and in this probability is the probability that 3 or more people living there. I put it 3, but it should actually say 3 plus. 3 or more people living there, given that it's owner occupied, that was 0.420. And then the other 3 numbers for the renter row are shown. These are the conditional probabilities. All right, and all these numbers fill up the tree diagram. Now notice for each of these main branches, if you see the 3 branches here, notice that these 3 numbers add up to 1. They should, right? These 3 numbers add up to 1. 0.65 over here and 0.35 to 1. All right. So the first question was, what's the probability that if you selected a unit at random, that was renter occupied and there was exactly 2 people living in it? That's probability of R and 2. Well, that we use the multiplication here. Probability of R times the probability of 2 given R. So probability of R is down here, 0.35. The probability of 2 given R is this number here, 0.261. Multiply those 2 numbers, 0.09. Second question, what's the probability that 3 or more people live in the unit? If you select the unit random, what's the probability that 3 or more people live there? Well, it has to be the sum of 2 disjoint probabilities. It's a probability that 3 more people living there and it's owner occupied, or, which is a plus, the probability that 3 or more people living there it's renter occupied. So it's the sum of these 2 joint probabilities. And how do you, now, this joint probability, 3 plus and W, it's simply, if you go along the tree diagram, it's simply the W, 0.65, times 0.42, right? You can see it, right? It's just this branch and this branch. If you multiply these 2 numbers, you get this one. The probability 3 plus and R, you have to go down to the R branch, and then go along this little branch here, the 3 given R, 3 plus given R, and you multiply these 2 numbers. And then you add it all up, you get 0.405. Okay? So that would be the sum of, so 3 plus would be the sum of these 2 numbers. It would be the sum of the multiplications numbers here. Now, I didn't show you the end results here, but one thing the textbook does, which you could do also with the tree diagram, by the way, is you can simply just multiply across, right? Multiply W times 1 given W and get your answer. W times 2 given W, get your answer. W times 3 plus given W, get your answer. And so forth, and get all of the 6 numbers out here. Those are the joint probabilities. And then you can simply pick out the answer, right? You can just run your, if it says what's the probability of R and 2, you just simply go R2, and then the number that's out here, the multiplication of those 2 numbers is your answer. 3 plus would be, well, it's 3 plus is over here, and it's also over here, and you have to multiply these 2 numbers. So the number that's the result of these 2 numbers being multiplied, to 0.65 and 0.42, plus 0.35 times 0.37, this number, the sum of those 2 ones, let's say 3, the sum of those would be the answer to B. All right, so if you decide to use a tree diagram, you may not even need to use the formulas here if you know what the tree is representing. So 3 plus would be the sum of the result of this multiplication here plus the result of this multiplication here, these two branches. Okay. Now the third one said, what's the probability that if you know, what's the probability if you know that the housing unit only has one person, what's the probability that it's being rented? That's really what the is being asked here. Now, this is very interesting. This is where Bayes' rule comes in. All right, because you can, and the formula sort of has to be used here a little bit. It really does, so that because the what the tree is giving you here, if you wanted to know something, it would be the reverse of this, right? You're given from the table that the probability of one given R is 0.362, but you're being asked for the reverse of it. So this is where the Bayes formula would be useful. So you could write the conditional probability formula now. Probability of R given 1 is probability of Rn1 divided by the probability of 1. Now the numerator, because we are given the probability of 1 given R here, which is the reverse of what we're trying to find, we can convert the numerator into the using the product rule or multiplication rule. We can use the product rule so that we're using the reverse conditional probability. It's the probability of R times the probability of 1 given R. Okay, because that's what's given in the tree. The denominator is the probability of 1. By the way, if you wanted to, you can write everything out and just plug in the information from the numbers that are given, or you can leave the probability of 1 there. And the numerator, and the only thing you have to do is convert the numerator. So it could be the probability of R times the probability of 1 given R divided by the probability of 1. Now, what would be the probability of 1? Your denominator. Well, that's the total probability rule, but that's given by the tree. The probability of 1 would be is if you multiply these two numbers, 0.65 times 0.217, and then add to that the probability of 0.35 times 0.362, you will get the probability of 1. So the result of the multiplication here and here, if you add those two numbers up, you get your denominator. Easy. You don't even need to do all of this conversion. But the numerator, you really should. Now, the probability of R times the probability of 1 given, okay, is Rn1. Oh, wait a minute. Wait a second. Even that I didn't need to convert, did I? Because the Rn1 is the result of the multiplication of this branch R and 1 given R. Oh, so if I multiply all these numbers out, like I suggested you do, I don't show it here, but if you multiply them all out and put them over here, then you don't even need Bayes' formula. You just need to use the formula for conditional probability. The numerator is simply going to be the multiplication of 0.35 times 1 given R. 0.35 times 0.362, that's your numerator. Your denominator is going to be the sum of the 0.35 times 0.362 plus the other branch up here, 0.65 times 0.217. That's the other one. It's 1 person. Okay. And the sum of those two numbers gives you the denominator, and then you just divide and okay. I showed you all the actual formula, but again, you could have just skipped this step with all these conversions here and simply use the tree diagram and multiplied everything through, and you would have gotten this answer, 0.473. All right. Let's go back to the textbook. Share again, the textbook. Just give me a second. Here we go. Now let's go to fifth P57. This is another example. And this is similar to the mammogram example that they showed in the book, in the PowerPoint slides. It says the mammogram is helpful for detecting breast cancer in its early stages. However, it's an imperfect diagnostic tool. All right. According to one study, 86.6 of every 1,000 women between the ages of 50 and 59 that do not have cancer are wrongly diagnosed. So that's the false positive information. Okay. Every 1.1 out of 1,000 women between the ages of 50 and 59 do have cancer are not diagnosed. That's a false negative. 1 in 38 women between 50 and 59 actually have breast cancer. If a woman between the ages of 50 and 59 has a positive mammogram, what's the probability that she has breast cancer? All right, so this is the information that's given. Now, when they say 86.6 out of every 1,000, you simply divide that. You just move your decimal point to the left by 3 decimal places. That would be 0.0866. When they say 1.1 out of every 1,000 women, that means you take 1.1 and move the decimal point 3 to the left, 0.0011. And then 1 out of 38, you simply divide those two numbers, and I would round it to 3 or 4 decimal places, probably 4 decimal places. And that would give me the numbers that you can use for your tree diagram. So what are they asking for here? They say, what's the probability that the person will have breast cancer if they have a positive mammogram? So, all right, so let's take a look at the example that I am showing you, or the result, the solution that I'll be showing you. Okay, so let's actually go to that page. This is page 50. This is problem P.57. Same page as the other one. Easy setting up the events. 2 events are the B, person has breast cancer. D, for diagnostics. The mammogram indicates a positive diagnosis of breast cancer. So it's a diagnostic result. All right. So B is the probability that if you selected somebody at random, person has breast cancer. D is the positive result of the test. Now, what's given in the problem? Okay. This is the false positive probability. 86.6 people, or ladies out of 100. What did they get 0.6 from this system? So 86.6 ladies out of 1,000, okay, have breast cancer. Excuse me, not breast cancer. Have a positive diagnostic test, but in reality do not have breast cancer. This is a false positive. So again, it's 0.0866 if you convert it. The second probability is the probability that they have a negative result from the diagnostic test, but they actually have breast cancer. That's false negative. That's 1.1 out of 1,000, 0.0011. And then the probability in general that in the population that the lady has breast cancer is 1 out of 38, which rounded to 4 decimal places. I would recommend 4 decimal places, 0.0263. So everything's in 4 decimal places here. And you're being asked, what's the probability of B given D? Now notice that up here, you see the probability of not D given B and D given not B. Notice it's in reverse of what you're being asked to find. So you need to, when you find this probability, you need to use the conditional probability equation and then use the tree diagram. So let's look at the tree diagram so that you can see exactly how this is set up. Now, 1 out of 38 is 0.0263. That's the probability of having breast cancer. Notice I put that first. I put the disease and non-disease first. the unconditional probabilities. So 0.0263 is a probability in general in the population that he does not have breast cancer. So 1 minus that, 0.9737, is the probability that they do not have breast cancer. Now the false negative is the probability that the diagnostic test shows negative when the person actually has breast cancer. That's this branch here. So that's the 0.011. It's 1.1 out of 1,000. And then the false positive would be that the diagnostic test is showing the person has breast cancer when they actually don't. So that's where this shows up. And that's the 86.6 out of 1,000, or 0.0866. Now we have three numbers. Remember with these examples here, when we have an initial branches here, and then we have two branches that branch off from those. We only need three of the numbers to fill out everything else. And what are the three numbers? We know 0.0263, we have 0.0011, we have 0.0866. So this number here is 1 minus 0.063. This number up here is 1 minus 0.0011, and then down below here, that this number here is 1 minus 0.0866. So we have all the numbers that we need. Once again, I did not show you the numbers that would occur if I multiplied all these through. So if I multiply 0.0263 times 0.9989, that will show that number here, but you can do this on your own. When you do these problems, you can multiply them through. You should have four numbers out here. And those are the joint probabilities, which you can use for solving this problem. So the problem is, what's the probability that if you get a positive test, what's the probability you actually have breast cancer? Okay, that's what this probability is. And again, it's conditional, so you create the conditional probability. The numerator is the probability of B and D. So that's B and D. That would be the multiplication of these two branches. It would be B and D. So it would be 0.0263 times 0.9989. That would be your numerator. And the probability of D would be the sum of that number plus the probability of not B and D given not B. That would also be a probability of D. So if you multiply 0.9737 times 0.0866, and if you get that number plus the number up here, which you put in your numerator, gives you your denominator. And that's it. But what I did here is I showed you Bayes' formula, and I multiplied everything out. But if you just simply multiply all the branches through, and then simply add the two branches that you need for your denominator, which is your denominator is probably D, so you need this branch, these two branches multiplied, and these two branches multiplied, these two here. If you add these two numbers up, that's your denominator, and this branch here, the multiplication of those two numbers gives you the numerator, and you're done. So that's it. It's obvious to me that tree diagrams are useful for doing Bayes' formula, for doing other types of total probability questions, things like that. So using multiplication rule, everything that we've learned so far. Hopefully this helped a little bit. Please read. You still should read the text in the ebook. Read through the examples. Go through the PowerPoint yourself, or the other examples that show you in the PowerPoint. There's plenty of examples here. This should prepare you to do the homework. And then typically on my test, I will have a Bayes type question on the exam. So it's good to know how to do this so that you can get those points. All right, so I wanted to show this to you so that you can have the opportunity to go through this multiple times if you'd like to help you solve the problems in section P2. So on the next meeting, we won't be going over this. We'll be going over section P3. All right. So I hope this was helpful. I'll stop the recording now and have a good day.